I invite Dr. Ashad Hussain sir to chair this session. Dr. Ashad Hussain sir.
Thank you, Dr. Danish. And we have assembled here to have this next session of Atal AICT Faculty Development Program and Advancement Lab for Scientific Computing. The next presentation would be done by Dr. Soumya Jyoti Rai, who is an assistant professor in the Department of Physics from IIT Patna, Bihar. And he will be making a presentation on scientific data analysis and visualization using MATLAB. So I would like to give a brief introduction of Dr. Soumya Jyoti Rai, who has joined us. I welcome you, sir. Dr. Soumya Jyoti Rai is currently working at the Department of Physics, Indian Institute of Technology. After completion of his master's from IIT Kanpur, he moved to United Kingdom for his PhD from the University of Andrews, UK, and worked as a research scientist in CEA, France, and Technical University in Germany thereafter. His current research group at IIT Patna works in the area of spintronics, bioelectronics, and energy, which gets covered frequently in high impact journals. Currently, he is serving as also as a PhD coordinator, nodal officer for student database creation, professor in charge, student registration, professor in charge, faculty. He is also a popular scientist reviewer, serving as editorial board member and member of grant review panels. He has received various awards, including the Career Research Award, DST Inspire, Faculty Award, and Research Excellence Grant Award, the European Metrology Research Program in recent times. He has also delivered lectures at University of Cambridge, University of Oxford, University College London, University of Leeds, University of Glasgow, Scherer Institute, Switzerland, University of Twente, Netherlands, Helmholtz, Zentrum, Berlin, Planck Institute of Microstructure Physics, Germany, etc. So we are pleased and honored to have you, Dr. Soumya, with us. And I'd like to request you to please start your presentation.
Thank you, sir. And thank you, Dr. Danish, for this invitation and giving me this chance to talk to the participants on this platform. So I'll share my PPT here. Good morning, everyone. And thanks to all the participants for taking your time and attending this session. And thanks to Mohd Danish also for giving me this opportunity to talk on this platform. And thanks to all the organizers for organizing this nice event. And sorry for the little delay in getting this thing started. This is the first time I'm experiencing this thing. I don't know, probably there's some problem with my computer. Anyway, so without wasting much time, I'll start my presentation. So the title of my presentation is Scientific Data Analysis and Visualization using MATLAB. And my name is Soumya Jyoti Rai, and I'm currently working within the Department of Physics at Indian Institute of Technology, Patna. So if you have any question, you can please wait till the end, and then or maybe you can write it in the chat box. So we'll take it at the end. Okay, so now before going into the presentation, so I'll first give a brief introduction of the institute where I'm currently working. So this is a second generation IIT Patna. It is located around 35 kilometers from the airport. And here we have basically 10 departments right now, and around 150 faculties who are working, and around 2,500 students are currently enrolled. We have BTech, MTech, MSc, PhD, all these programs are running. And we also have an incubation center where people with any new idea of product development, they can work, they can get some seed funding, and also they can have some sort of like mentorship, these sorts of things, facilities they will get. And also they get some salary also if their proposal is successful. And recently one technology innovation hub has been established. So this is in support with Department of Science and Technology. So this is mostly on artificial intelligence, natural language processing, these themes. So on the right hand side, you can see this aerial view. So this is a picture which was taken with a drone, I guess. So this road is the road which is going to the main gate, that is the approach road. So on the left hand side, if we go to the departments, and on the right hand side, if we go, then this road actually enters into the residential area where we have hostels and then residences. So it road actually goes quite far away from here. And this is the main building, main administrative building. So where most of the administrative offices are located. And the building at the bottom, so this is block 4 where I am located currently. So right now I'm sitting in one of the rooms here actually this side. Okay, and next, so the research group which I'm heading here, that name is Quantum Materials Group. So we are mostly working with quantum mechanical properties of different materials. So here are the photos of some of the members. So on the left hand side, these are the people who are currently working with me. And on the right hand side, these are the people who have recently graduated. So these people who have graduated, they're mostly now all over the world. They're like some are in UK and in Canada, US, and also in industries. People are kind of there in different places. And the research area which we are doing is in the area of nano electronics, spintronics, memory, sensing, and energy. So electronics we already know. I think most of you are also kind of expert in this thing. So nano electronics is basically an extension of that. So we are mostly working with much sophisticated electronic circuits. And spintronics is also like it exploits mostly the spin part of the electronic property or electronic circuits we are developing with let's say like mostly exploiting the spin degrees of freedom. And memory, we know that there is a constant demand of memory. So like we have RAMs and hard disk, everything. So we are also working on that. And other two areas are sensing and energy. So these are also some of the areas which are very much relevant for the present context. And we are working with different materials, and we are working with basically you are using a combination of theoretical and experimental tools. So different modeling tools we are using, and multicolor simulation, molecular dynamics techniques we are also using, and experiments we are also doing. So part of this device modeling and data analysis part, we do use MATLAB. So I personally started using it quite some time back when I was a student, and now I mean I don't actively use it that much, but I do use it from time to time. Okay, so now coming back to the content. So MATLAB, as you know, the full form is Matrix Laboratory. So it is a numerical computing environment, and it is a proprietary programming language which is developed by MathWorks. So it's a commercial program, and you need to get a license basically if you want to officially use it. Now, the best part of MATLAB is that it allows you to do certain mathematical or let's say graphical operations which are not commonly available in basic or let's say fundamental computational programming languages. So one of the basic one is matrix manipulation. And this is like a lifesaver. For example, people who have used Fortran or C or C++, they know like how much time it takes to just define a matrix and do any kind of matrix operation. But here MATLAB allows you to do this thing in maybe one line or half a line, something like that. So I think in the talk which you just had before me, there was quite a lot of these details are covered, and you have probably got a glimpse of this thing. Next is plotting of functions and data. So this means this is the part of data visualization. So you actually have plenty of functions which are inbuilt and available in MATLAB. So you can directly use those functions, or if you want, you can also define your own function, and then you can use that for your own kind of need. For example, if you have some data, if you want to do some analysis, there you can use it, or if you want to plot it, there also you can use it. So some examples I will show you, like some particular case study we will take care of today. So where I will present one of the examples where I have used MATLAB to analyze some of the data of like my work which I did in the past. And then you can also implement different algorithms. You can also create different user interfaces, like graphical user interface you can design. And then also you can interface with different programming languages, which like if you have already written programs like in other languages, that also you can incorporate and you can interface with that. So it gives you a lot of flexibility and freedom. And that is quite a big thing actually. I mean, in terms of user friendliness and kind of operational kind of smoothness, MATLAB is quite good. And one of the major advantages, as I mentioned already, that some of the powerful operations, it can be done with just 1 or 2 commands, and you can build up your own function. So combined with the graphics facilities, and you can also do document processing. So I'll just give you a small example at the end, how can you do document processing with MATLAB. And that basically like covers an entire spectrum of things which you mostly need to do in, let's say, teaching or research. So if you are proficient in MATLAB, then you don't need to actually look into quite other things. Actually, most of the things you can do with MATLAB. Okay, so now basically, so the plan of the presentation is that, so today we'll first start from the beginning and then we'll slowly go step by step. So I'll first talk a little bit about the MATLAB interface and the data and how can you do things, and then I'll take some case study, and there we'll go a little bit into details, and depending on the time available, we'll probably take 1 or 2 case studies. So 1 at least I'll cover, and if we have sufficient time, then I'll cover another case study where I'll show you how MATLAB can be used for different examples, I mean different kind of situations. So here, this is the workspace. That means if you open MATLAB on your computer, it could be desktop computer or your laptop, you see this kind of view, but this actually changes from version to version. So this one is taken from, I think, either probably 2024 version. Okay, so here I think in the latest versions also things will be more or less similar. Maybe the layout has changed a little bit, but you can see there are few tabs which are open. So on the left hand side, you can see this is current directory. What does that mean? That means this is the working directory or the folder where you are going to do the operations or store the data or save things like that. So here you can see this is the path where you are currently working in. And then in the middle, this is the main part, which is called as command window. So here next to these double arrows, you can type all the commands, and those commands will be executed depending on whether the commands are correct or not. If it is wrong, it will give you a message. If it is correct, it will be executed. Or if it is partly executed, that information will also be passed to you through MATLAB. So that is done here. And here also, if you are quite unclear about something, for example, let's say if you want to plot it, plot some particular function, or if you want to write about some particular graphics, then you can simply type help, and you can press the tab, and then you can just type 1 or 2 characters, and then you can see all the help files will be available here. And it has excellent help files which are available in MATLAB. I mean, that is one of the big advantages here. And with clear examples, you can get an idea of what sort of things you can kind of like do or use, and kind of like what are the functions that are available. So it will be quite good help. And in general, actually, if you look at on the top part, there is this search bar where also you can type and then you can get the search documentation. So that is also available here. Now on the right hand side, there are 2 tabs. So on the top, it is workplace. So here, if you see, there are 2 variables which are stored here, x and y. And x has some value which is written as 1 cross 101 double, the minimum and maximum. So let's say if I create a variable, or let's say if I create any other quantity, or most likely let's say data sets, they will be available in the workspace. Okay, so these are like, let's say, the objects which are containing data. So it could be text files also, or text information also, but these are objects which have some sort of data that will be stored here. And if you want, you can simply double click on them, and they will open. Like you have other plotting programs like Origin, you can also get to see them. So that facility is also available here. And here it tells you that what is the size and what is the minimum, maximum, and other properties are also available here. If you want, you can just add and remove them. And at the bottom, this tab is called as command history. So whatever commands you write in the command window, it gets stored here. Or this is the history file, like you have in an internet browser, the histories are stored here. Also the history will be stored. So you can check it in the settings that how long or how much amount of history you want to store here. So that will be kind of, that will be determining how much information will be stored here. Now this is actually quite helpful here, especially suppose if you have a custom made program, or suppose you are working today and then you somehow had to leave, and next day you are starting again, and then you want to go back to the command which you used probably yesterday at 2 p.m. So what you can do is that you can simply browse through this command history, and if you just double click it, it will automatically be executed. So you don't need to retype the commands again. Okay, so this is a very useful advantage. And commonly what I used to do is that I used to take a copy and paste these things in a Word file or let's say text file and save this so that okay, so basically this command history I used to save so that in future, if let's say I am working on a particular project and then I'm moving to another project, so sometimes I don't always remember what exactly the command I was using earlier. So if I just save this command history in with some specific date and some appropriate file names which are good for my memory, then they can be quite handy also. So you can think of it as some sort of a logbook. Okay, so these are the different parts of and MATLAB active user interface, and here also you can see there are several kind of icons which are available, like new. So I think if you click on new, you can see the new M file, that means the MATLAB file, or new data, or with open you can open anything and then you can import data, you can save workspace. So this is a very useful property of MATLAB, that whatever you have in this space, that means mostly let's say this in the workspace, suppose you did some analysis and then you created something, so it could be figures or anything, and some data has been produced as a result of that. If you save it as a workspace, so those workspace will basically the workspace will be saved and it will contain all the informations that are here. Okay, and other than that you have new variable, open variable, so these are self-explanatory. And now actually there is another useful point which I think I should mention here, that in the preference actually you can go and there are several parameters you can change. So these are again your personal choice. Sometimes some people like this particular font, some people want to change the spacing, some people want to change something else, and also you can drag and drop these windows also, like these tabs, so that you get a look which is more useful for you. And then set path. So this is actually an important kind of like a property of MATLAB. You can say that sometimes MATLAB by default opens in the path where it is installed. So like see my computer, something like some application folder, it opens actually. But sometimes your working directory, like your data is not stored in that folder. So in that case, you need to set the path. Otherwise, your comments might be correct, or your functions are stored in the proper kind of place, but your whenever you are trying to execute, MATLAB might not be able to find it out. So this case, you have to set the path. So if the correct path is available, then MATLAB will be instantly able to recognize this thing. So these are some of the know-how of MATLAB. Now, I'll come back to the opportunities. So this part is mostly interesting for students and graduates. So what are the advantages of learning MATLAB? So somebody can say that, oh, if I learn Python or some open source language where I can have some advantage, what is the advantage of MATLAB? So there are some clear advantages that if you learn MATLAB, then you can have quite a lot of benefit in these areas, like you know about modeling and simulation, algorithm development, scientific graphics, data analysis, and exploration. So these are the things which you will be master of if you know MATLAB correctly. And there are several companies in India which hire engineers for their MATLAB skills. So some examples I have taken from Google. There are companies like Cummins, Tata Motors, Infosys, Tata Consultancy Services, John Deere, IBM, Cognizant, Tata Technologies, and you can see Mahindra, Accenture, Siemens, then Wipro, and then Slumberger. So there are lots of organizations, which are like big companies, who actually want to hire engineers, or let's say people with MATLAB skills. So if you genuinely know how to use MATLAB, then you have a very good chance that you might get a job in any of these companies if you're interested, of course. Okay, so now in these particular presentations, we will be talking about mostly data. So am I audible, by the way? Hello?
Yes, you are audible.
I'm audible, right? Okay.
Yes, yes.
So in these particular presentations, we will be focusing on these areas, like the use of MATLAB for scientific and engineering needs. So these are mostly academic, let's say. And we will be looking at how we can do numerical simulation, calculation, programming, and modeling. And in that process, we will look at how to solve equations, data analysis, producing graphics, and GUI building, and document preparation. So we'll try to look at these aspects. So now, before getting into this, let us look at data, some of the basics of data. So the very early idea of data to us comes from our school days. So probably in our high school, when we are doing some experiment in physics lab, that you are probably switching on a light bulb, or let's say it could be a chemistry laboratory where you are doing a titration experiment. So you do have some experiment and then you take some readings. Okay, so you do data collection. So this is the first step of the work where we get introduced to data. Next, what we do is that we do tabulate this data in some sort of a form like this. So we have an independent variable, we have a dependent variable. So that is the most simplest form which we do store the data, and then we can plot actually. So this is a line plot where you can see how does the dependent and independent variable are related. That pattern we can get from this data. So this is the very basic idea of data, how it was introduced to us. And now let us look at how data can be manifested in our life. So here I will take an example. So this object you are mostly familiar with. So this is a landline phone, and there used to be a telephone directory where all the telephone numbers of the city or town are used to be printed here. And if you want to look at this phone book, then you can see that each of these numbers used to kind of like relate to some particular household. Okay, so it means that each of these houses has some particular number. So this is a data. Each house is represented by one particular data. That could be a 6-digit or 8-digit number. Within the house, what do we have? We have a family. So we have maybe some kids and their parents and their grandparents and some pets. So these are all the members that are located inside these houses. So we can say one single number, let's say few digit number, is representing this entire entity. So this is on data. Now, if we want to make a phone call, what we'll do is that we'll take the number from there and then we'll make a phone call to the other person. So from one house to other house, this is going. And in this process, data is transferred. So this data could be anything, like it could be your personal information, it could be your work related information, anything. And sometimes all the members can be involved in that process. So data is being transferred and that gets transferred through this process, and members, different information can be transferred. Now, in the present day, so the newest data, it changes a different form. So now we have a mobile phone, and if you look at it closely, then we can see there are multiple apps in our mobile phone. So some are for storing our files or data, some are for writing emails, some are for social networking, where you have all your day-to-day activities that are listed. Some are for only messaging to another person. And then there is app for, let's say, driving, where it stores your current location and the path where you are traveling. Then you have photo, and then you have your travel history that is being stored in different apps. And then you have your video information and your, let's say, health information, like how much you have walked or maybe how many steps you have kind of covered today. And then you are doing online shopping. There also your shopping history is being stored. And let's say you are watching some videos, so your music preference, that is also being stored. Then your banking information, credit card, so everything is there. Okay, so now if you look at earlier, but it used to be a single number. Now each member of the house has a mobile phone, and each mobile phone has this many apps, which means that each person provides that much amount of data for different needs. So the volume of data, it has grown up manyfold. Okay, and because of this reason, there are companies which are paying huge amount of money to collect this data and use it for their market survey and developing their portfolio, building their future market research, things like that. So the data has become such a big area that we are now in a situation that we can compare data with new oil. So maybe 30 or 40 years back, when oil was discovered, that time people used to say oil is everything which controls the our economy, or let's say the world's economy. And in the present day, it is the data. So data could be anything. It could be raw survey data, it could be log files from your computer, it could be employee data, it could be customer information, it could be emails, it could be anything. However, it is information, and this is the new oil, which means that whoever has and hand on this data, that person is considered to be very powerful in the present day. And that gives rise to this industry, which is called as big data industry. And you can see basically there are several areas where this is quite prominent, like the area of energy, where the asset optimization, that means which kind of energy is being utilized and how to do the optimization. That information is quite relevant in this area. Then finance, where people used to investigate market risk, regulatory, and how the market is going to behave, things like that. Then we have automobile industry, where the driving pattern analysis, so fleet data will be quite relevant here. Then aerospace, there the maintenance and reliability, and in medical devices, so this is a really fast growing industry where the information of the patients will be quite relevant. That means if you want to know that what type of disease is particularly happening in a particular part of the country, or let's say in a particular kind of segment, so those informations can be very, very beneficial for future elimination of those diseases. So data is quite big, and as a result, there are several data kind of like entities which have come up in the data ecosystem. So one is called as big data, which I just explained. Then we have neuromorphic computing, where the computing, that means the data patterning or analysis, is being done through a computational framework that mimics our brain. That means the way our brain works, it also does the same kind of mimicking. Then you have 5G, which is used for transferring this data from one end to other end. And then we have Internet of Things, which actually connects all these different objects through internet and kind of makes it unified. So you can see this data ecosystem is quite big, and we are in an area where this is very, very prominent. Now, if we look at this data market, then we can see that how this data market has grown up over the years. So in terms of US dollars, you can see in 2011, it used to be less than $10 billion, and sitting at 2021, we have around, let's say, $70 billion. So it has grown by almost 10 times in the past 10 years. And it is also expected to grow at a similar rate over the next years. So the data is becoming more and more bigger in volume. And as a result of that, the amount of jobs which are related to data analysis or data scientists, they are also increasing. And here you can see there are different categories like analysis, machine learning, statistics, computer science. So these things are also coming up. And once you have the data, you need to store it, which means that there has to be a need in the increase in the storage capacity. So that has also exponentially increased over the years. So in the past 10 years, you can see that there is a very sharp increase in the amount of storage space. Now, why I'm talking about data is because MATLAB is explicitly something which handles with the data. Okay, so that is the end of first part. I hope you get some overview on the data architecture. And now we will talk about the part where we will show how data analysis can be done, let's say, from a scientific perspective. That means for, let's say, our college life, or let's say if you want to write a paper, or if you have, let's say, any kind of data, if you want to analyze, so it could be for some company or industry also. However, how they can be done, that I'll show you with MATLAB. So here actually this is a figure which I have taken from a Nature paper. You see this has been published in the year 2013. So you know Nature is like a very good journal, and it has a very high impact factor. So it is very difficult to publish in this journal. And this specific article was published by a Nobel laureate. I mean, this particular work was not the Nobel Prize winning work, but this is somehow related to that. But the reason why I am showing this figure is because I want to take an example of how, let's say, the top of the areas, the people who are there, how do they represent the data. So here you look at, there are 4 figures. So in figure A, you can see this is a color figure. So we have X and Y column, and this is basically a 2D color plot of, let's say, some particular entity. So I'm not getting into the technicalities, but you can see there are basically blue areas, and then there are some yellow and green channels. So these are some artifacts of the system that they're investigating. So, but the point is that the raw data which they have obtained is not anything close to this. So the raw data probably some noisy oscillations or something, and they have done proper data analysis and kind of smoothing. And after that, if you make a phase diagram kind of thing, let's say if you have a 3D data and then you are kind of like contemplating everything onto a 2D plane, then you probably get something like this. And the usefulness of such plots is that it will clearly tell you, or you can clearly get the information of what is happening at which point. Let's say if I want to know at this magnetic field what is happening, then I know, okay, I'm getting this yellow line. So that probably corresponds to some physical scenario. However, the important point here is that the representation is something which is quite different from the actual raw data. Then in the bottom, you can see another very nice colorful image. So this is again a 2D projection of a 3D data. And you can see there are two independent variables here. And you can see there are also these blue channels which separate these kind of purple or let's say red areas. And on the right hand side, we have line plots. So these are like Y versus X plots. So there are two colors. You can see there's a black color, there's a red color line. And in some areas they're overlapping. And there are some plots also which looks like, let's say, some graphics. Okay. And here again, we have some colored images here, and then we have some line plot. So in this graph, basically, we have everything that we have line plot, we have 2D plot, we have 3D, and then we have some graphics. And we'll try to look at how each of these can be produced with MATLAB. And some of the processing I'll show you. Okay. So now, let's say the first thing we'll talk about the line plot. So in MATLAB, if you just want to do a plot of a line function, so here, let's say I am trying to plot the sine function, then what I'll do is that I'll take the independent variable that is, let's say for sine x, so x is the independent variable. So here I'll take a range that is 0 to let's say 2 pi, and I'll kind of like span the space, that means the interval between 0 and 2 pi into 100 equal kind of spacings. Okay, so I'll have 100 points, and that will be given by this particular function, lin space. So lin space means that linearly it will create a spacing between the initial and final value. So I'll have that, and I just write simply y equal to sine x, that will calculate y. And if I type plot x and y, so this is a very simple command, you can see, and it will give me this kind of plot with automated whatever the values are there. Okay. Now I can plot more than one graph also. What I have to do is that if I create two variables, that means y1 and y2. So let's say y1 is sine x and y2 is also sine x, but it is shifted by a phase that is pi over 4. And if I plot x y1 and x y2, then I will have both of these graphs automatically plotted on the same graph. So there are other ways to plot this thing also. So if you type something called as hold on, that is a command, then also it will hold any future plots on top of this graph, unless you say hold off. So then it will stop doing that. Okay. So you have this plot, and you can see they are of different colors. However, this color is not specified here. So what MATLAB is doing is that it is kind of efficiently recognizing these two are different plots, which means that there should be some different colors which it is automatically allocating. However, if you want, you can also put the colors by hand yourself. So all you have to do is that you have to put a comma, and then you have to put, like, let's say B, that means let's say black color, or let's say R, so within a column that will be red color. So I'll show it later, that there is a table where I'll show which color and which symbol is there. Now let's say these plots can be done through different ways also. So this is a dotted pattern, this is a symbol only, that is a star symbol, and here basically they are dotted pattern, but the patterns are different for two different graphs. Here also it is same, and in this case this is dotted plus symbol. So all different options are available in MATLAB, and depending on the choice and you can choose whichever you want to plot. Now I'll go to 3D line plot, where what I'm doing is that it's a line plot, but it represents a 3D behavior. So now what I'll do here is that, so let's say the range that I'm interested in is 0 to 10 pi. So as you can see, it's a 3D line plot. That means, excuse me, I will have to have basically two different axes. Okay. So here basically I have st and ct. These are the two functions. So one is sine of t, other is cosine of t. And if I use this command plot 3, that means it's a line plot in 3D with these three variables, then I'll get this kind of a pattern. So you can also choose other functions. For example, instead of sine, you can choose here cosine, and you can choose sine here, and you can choose like exponential function. You can see anything. However, the final plot or outcome will be dependent on the type of function that you choose. But the function that you need to use here is plot3. Now you can also draw a parametric line where, let's say, instead of giving like a particular value here, you just say that t is the parameter against which I want to plot. So here x is sine of t, y is cosine of t, and z is t. So these are three variables which are function of time, and I have a default range -5 to 5. So all I have to do is that xt I write is that t sine t, y2 will be t cosine t, and z2 will be @t and t. And if I use this command f of plot3 x t y t z t, then I can plot all these three. That means this particular trajectory is a representation of all these three functions overall. So it is not representing one particular function. X, y, and z, they are represented together in this particular plot. Now here are some other options. So you can also plot bar graph. So bar graph is commonly used for, let's say, if you have a steady increase in one parameter, that, like, let's say it could be like the temperature increase of one particular city, or let's say the increase in population, or let's say the increase in the marks, or any kind of parameter like that, where bar graph is quite actually relevant. So you can probably see it in news channel. These graphs are sometimes used. So all you have to do is that, let's say you have a column which is y equal to these data numbers, and all you have to do is that bar and y. So you need x here. So x it will take automatically. So you can see these indices 1, 2, 3, 4, 5, 6 up to 11. It is taken automatically. So the way these data points are included in this y vector, the bar plot will take that and it will plot this in an increasing order. And similarly, if you want to plot this bar over a specific x range, let's say you have certain numbers and you say between 1900 and 2000, how did that number change? Then you can also assign the x-axis or x scale here. So all you have to do is that x you have to define and y you have to define, but make sure that the number of points in x and number of points in the y vector, they're same. Otherwise, it will not execute. So then if you type bar xy, then it will give you this kind of a plot. So here in the second graph, you are putting the x by hand. Now there are other types of plots you can do. For example, you have a pie chart where, for example, if you want to represent what is, let's say, a particular share of, let's say, one particular quantity compared to the overall volume. So let's say, for example, very simply, I can say that, let's say, if you want to take a voting of something, then you can see like either it is 50-50 or let's say 60-40, or it could be like you have, let's say you are taking a poll on some particular things and you have three different answers which are available. So clearly you will get three different kinds of vote. And if you know the answer, then basically all you can do is that you can use a pie chart to represent these things. And that clearly tells you who has the larger volume of the pie. So here you can see that you have 1, 3, 0.5, 2.5, and 2. So there are 1, 2, 3, 4, 5 elements are there, which means that this entire space will be occupied by these 5 numbers. Okay. So as you see that some numbers are large, some are small, and depending on that, it will get a particular fraction. So 33% is the highest one and 6% is the lowest one. So that probably is coming from 0.5. So all you have to do here is that you have to define this x vector and type this command pi of x. Then it will create you this plot. And this 3D pie chart you can also do. So this function will be a little bit different. And here also it will give you a little bit of different view of this pie chart. And then there is another type of plot. This is called as a polar plot. So this is, let's say, if you have an angular variation of some particular quantity, that is nicely represented by this kind of plot. So let's say if your theta varies from 0 to 2 pi, and let's say you have another function rho, which is a function of theta. So let's say rho is a function, rho equals to sine 2 theta times cosine of 2 theta. Then all you have to do is that you have to type polar plot theta and rho, then you get this kind of plot. Okay, so these are different plots, and depending on the need, you can actually choose which type of plot is relevant for your particular analysis. Okay, so now let us go to another type of plot. So this is a 2D plot, and this is called as a contour plot. So a very basic example of a contour plot is that weather data. So you have probably seen on the news channel that during the monsoon season, or probably the direction in which wind is going to flow, and where there is to be rain, or where there will be, let's say, sunshine, that information is kind of being used. I mean, it is kind of displayed through the use of contour plots. So how will you do it? So basically, it is kind of a projection of a 3D plot on this 2D plane, and these lines represent like different. Let's say you have a 3D surface and you are projecting it onto 2D, so it will be a kind of like a complete loop. So it could be a circle, it could be a square, it could be a rectangle. So let us look at this example. Suppose here x I have chosen between minus 2 pi and 2 pi, and as I told you, lean space means that it will automatically span this interval into certain number of points. So if you specify it, it will take that number. If you don't specify, it will automatically take some numbers which is appropriate for your graph. Then you have y, which is also between 0 to 4 pi, it is varying. Next, what you do is that, so you have two independent variables. And here you are creating x, y. So this is a kind of vector, like within the bracket, you are creating something called as a mesh grid. So this function is quite useful. Mesh grid, within the bracket, you have x and y. So what I'm doing? So if I only look at x, let's say I have 100 points. So starting from minus 2 pi to plus 2 pi, I have 100 points. Okay, so here. Okay, similarly for y, I have 100 points. Now, what mesh grid is doing is that it is creating different points which contains both x and y. Okay, so that means I have x and y coordinates which is determined by this mesh grid, or let's say allocated by this mesh grid. Okay, so now I have, once I execute this command, I will have a 2D space where I have different coordinates. So it could be like 1, 1, 2, 3, 5, 6, 7, 9, things like that. And what the z will do is that z will take those particular values and it will take those coordinates to compute the value of z. And if you use this command, that is contour x, y, and z, then the z will be projected or plotted as a contour on this xy plane. Okay, so this mesh grid command is quite useful for any kind of 2D plot. Okay, so now you can also do this contour plot on 3D. So here actually you can see that you have, let's say if I have x only, that is varying between minus 2 to 2, then the mesh grid of I can create only with x. So here basically I'm using only x as x and y both. Okay, so the interval which is given here, I'm creating a lot of AB points like xy, xy, xy on this particular plane, and the z function is determined by this particular expression, that is x times exponential minus x square minus y square. So I have the value of z which is computed at different values of x and y, and these xy values, that means the points at which z will be calculated, have been determined by this particular function mesh grid. And if I use contour 3, so this is a 3D view of contour, x, y, z 30. So 30 is the number of contours that will be there. So then I'll get this kind of a plot. So earlier what I have is that, I have a 2D view, that means this is the projection. However, here if you look at, this is not the projection, but here is the actual 3D view. So if you want to use only contour command, then what you do is that these circles, or let's say these loops, will be looking like some particular circles, or let's say some ellipses. I mean some sort of a loop on this 2D plane. Okay, so next what you can do is that you can plot something called as surface plot. So here also you need this mesh grid. That means let's say you want to create a lot of x and y points, or points with x and y coordinates, and let's say the x will vary between 1 to 10 with an interval of 0.5, and y will be equally distributed between 1 to 20. And let's say the z function is sin x plus cos cosine of y. So if you have that, then you use this command that's called as surf, S-U-R-F. So if you do that, within the bracket you have these arguments x, y, and z, then you will get this kind of a plot. So this is the representation of this function, that is z, and you can see there are different colors which have been automatically assigned by MATLAB. And if you want to change the color bar, then also you can do it. So all you have to do is that you have to click on this color bar. So first actually in MATLAB you can see, once you have this plot, there will be a color bar option there. You click on the color bar and you can choose what type of color scheme that you want to assign for this particular plot. Okay, so now there is another kind of plotting function here. So let's say this is a which is available. So peaks means that it will automatically give you, it will automatically kind of like find out what are the peaks that are available from a particular XYZ data. Okay, so it identified and then you are using those peaks. So let's say here you have multiple peaks here. Okay, so it is identifying them and you are using this command SARPC X, Y, and Z. So then you will get a very nice kind of plot like this. And you can see if you can really put these kinds of plots into your report or let's say into your paper anywhere, they look very nice. Basically, if you can export into a very high quality with the proper color scheme, then it will give you very nice visibility. And as you see, this top plot is a 3D plot. However, in the bottom, you have different contours, which are again, these are the projections on 2D of this particular 3D surface. Next, you can do something called as GUI building. So GUI means graphical user interface. So far what I showed you is that you're typing the command and you are getting some result as a result of that execution. However, what you can do is that you suppose you have a particular script which you are using for a particular operation. Okay, so let's say here there is one example that is a robotic manipulator animation GUI. So you have probably a robotic arm and there are certain parameters which control which direction robot will move. That means either it can move up, down. So like different degrees of freedom are involved there. And suppose this script has been already written in MATLAB and this is the GUI which is controlled by that particular or basically supported by that particular script. So here you have a plug and play option. That means you simply click on this and let's say if you change the variables, so your robotic arm will move in a different direction and then you have different parameters. So depending on that, you can actually get that function without actually typing the commands or let's say without actually changing it. So it is kind of quite handy. Then a very simple one is actually my added GUI. So you have two numbers which you are adding. So here you can actually simply add like 1 plus 2 will be 3 or 10 plus 10 will be 20, something like that. So all you have to do is that you have to enter the numbers, you have to hit on the add button and you will get the result. Okay. Or also what you can do is that you can create a GUI which will give you a kind of like a plotting different kind of plots you can get. That is, let's say if you want to plot like if you have data set, so these are all 3D visualization. So let's say if you want to have sharp plot, so if you click on that, it will plot it in this sharp result. And then if you want a mesh plot, then you click on this, and then if you want a contour plot, you click on that. So that information, that result will be available here. So that facility, I mean, if you can create a GUI, this is a very simple GUI actually you can do. And we have also icons available here that are also can be useful. So this GUI can do kind of like quite useful if you want interested in these kinds of things. So here actually you can see this is the particular bar which I was telling you, like this is the color bar. So it tells you what is the maximum and minimum number which is available here. I mean that is used in this plot and what colors are being represented by that. Okay, so I see some questions here. So I'll come back to the questions at the end. Okay. Okay, so next is a subplot. So this is actually quite interesting. I mean, I personally find it quite useful. So suppose you have several plots which you want to make, and however, you want them to be in a compact form. Okay, so then this subplot is quite useful for that particular job. So let's say you have some plotting window, let's say 4 centimeter by 4 centimeter space, and you want to split that into 2 different plotting windows. So all you have to do is that you have to, so if you just type plot, then it will take the entire window, but subplot will take only a fraction of the window. So here what I'm doing is that I am taking this particular plotting window and splitting it into 2 parts. So one is 211, that is the coordinate, and 212 is the representation of the bottom part of the plot. Okay, so what I'll do is that I'll type subplot 211, which means that I'm telling, okay, whatever function I'm going to give you, you have to plot it in this top part. And then I'm giving some x and some y1, and I'm asking, so this is a sine function x, y1, it is plotting, so it's nicely plotting there. Next, what I'm doing here is that I'm plotting on subplot 2, 1, 2. Okay, so here on the bottom part, I am plotting y2, which is sine of 5x. And you can clearly see that sine of 5x has a high frequency. That means there will be lots of modulations or oscillations which are coming within the same x interval. So this is a very nice way of putting two graphs. And if you are interested, you can put or incorporate more than two graphs. For example, here there are 4 different subplots which are inserted. However, all you have to look is that how to assign the coordinates. So here you see these are different coordinates, 2 to 1, 2 to 2. So 2 to 1 will be this one, 2 to 2 will be this one, 2 to 3, 2 to 4. So the basic idea is that you are splitting this particular. So this is, let's say, your entire plotting window. You are asking it to split that plotting window into a 2 by 2 cell. So MATLAB actually thinks everything in terms of a matrix kind of thing. So let's say this is a 2 by 2 matrix. So you'll have 4 different, let's say, cells. Okay, 1, 2, 3, 4. So what will be the coordinate? So this will be 1, coordinate 1, this is coordinate 2, coordinate 3, coordinate 4. Okay, so 2 by 2 is the basic one, and then 2 to 1, 2 to 2, 2 to 3, 2 to 4. Okay, and this is the level which you can see here. The subplot 2 to 1, and then so on. And you are plotting different functions. And if you want, you can also use title, you can use different other things. And finally, if you want, you can export the entire thing. So this is a publication quality graph, and you can simply take it as in this particular form available. Now, in general, whenever you have one particular plot which is covered over the entire plotting window, or let's say you have multiple subplots, so there are certain kind of parameters which MATLAB takes into account by default. For example, there is outer position, then there is the inner position, and there is the position which is the end of the graph. Okay, so you can see there are these dotted lines, yellow, red, and green color that kind of represents this. And there are some ways to tune those things also, but you actually have to keep in mind that if you're plotting does not mean that your plot will be distributed over the entire space. And similarly, that thing is true for your subplots also. Now, as I mentioned earlier, that here is a table that actually tells you what are the different color markers and symbols which are actually useful for different plottings. So here you can see these are the colors which are available: B for blue, G for green, R for red, C for cyan, M for magenta, Y for yellow, K for black. So all you have to do is that you take the plot command, and before you finish the first bracket, so it could be any plot command. Let's say plot X, Y1, you put another comma and you put K within the, let's say, this comment kind of thing. Okay, like this kind of box. Within the comment box, you put K, then it will plot it into black color. And similarly, you have yellow, blue, green, red, everything. And then there are symbols where you have different kinds of symbols, and all you have to do is that. So most of these symbols are available on your keyboard. So again, you have to use the same method which I just explained, and like you have to put a comma at the end, and you have to put this comment like a bracket, and within that you have to put any of these, and then it will take that particular symbol as you want to plot. Other than that, there are also options of Greek characters, like if you want alpha, beta, gamma, then you can also use this particular kind of format. So these are kind of the way you use in LaTeX. Select /alpha, and also mathematical symbols like SARC, that means it will give a degree, PM means plus minus, and bold font, italic font, or superscript, subscript. So all these things are available, and you can simply use the commands which are generally executed in LaTeX here also. So let's say here you have an x-axis. Okay, so all you have to do is that double click here, and then if you type whatever mathematical symbol is there, it will automatically come up here. So here actually this is a summary of all the plotting functions that are available here. For example, if you want to do, so these are for 3D plots, then line graphs can be done through this, plot 3, contour 3, and contour slice. Then you have mesh plot, then you have pie chart, then you have SARC plot, And then you have actually direction dependent, like this is something which is like a wind direction, that arrows are useful, like quiver and streamlines you can see. And then you have these bar plots in 3D, then you have scattering data like volumetric plots. So there are lots of things you can see, and depending on the need you can actually choose these functions whichever is best suiting your requirement. And for 2D plots, you can also use different things like line graphs. You can use plot and then plot YY, log plot, semi-log Y. Semi-log Y means that you have only one Y-axis and X-axis will be in linear. Then you have bar plot, then you have area plot, then you have again direction graph, then you have angular plots and scattered plots, then histogram and then images. So there are different types of plots. Then you can plot error bar also. So these are different things, options which are available here. Okay, so this is the plotting part. So now I'm going to the next section. So here I'll talk about data structure. So don't get confused by this data structure with the data structure in computer science. So here I'll show you how data can be very efficiently used and manipulated into MATLAB without actually kind of losing track of things. Okay, so first thing is that, so here what we'll take an example. Let's say it's a real life example. Suppose somebody is doing an experiment, or it could be simulation work. So you are suppose doing some sort of a research work, or let's say project work. Okay, so you are interested in investigating some interesting properties. So usually what we do is that we study the behavior as function of several parameters. And what happens as a result of that is that you create multiple data sets under different conditions. And at the end, when you have the data sets, you need to analyze. So usually, I mean, when you're starting, we have small number of data sets, but if you're working, let's say for 3 months or 6 months on something, then you'll have a huge number of data sets. So typically, if the volume of the data set becomes huge, then you have to maintain a physical logbook to remember that, okay, which data sets on which date I taken and what it corresponds to, which becomes a little tedious task. Now I'll show you in MATLAB how these things can be done without actually doing much of these things. So it will save you a lot of time and effort. Okay, so everything can be included in the workspace. So I'll give you a very simple example. Let's say suppose you are doing an experiment, or let's say some calculation on one sample. Okay, so this could be a mechanical engineering sample, it could be a motor, it could be some kind of like a material, it could be anything. Okay, and suppose you have labeled these samples like S1, S2, S3. Let's say you have 10 different samples. So they are having different properties. So under certain different conditions, these samples are made, or they have some difference with each other. Now, each of these samples you have investigated on different days. So let's say on 20th January, 21st up to 25th. So let's say 5 days of the week you have investigated. And you take a particular day, you have checked the behavior. So let's say mechanical property you are investigating at different temperatures. So let's say the temperature range varies between 50 Kelvin to 300 Kelvin. So low to high temperature you have checked. And at each temperature, you have, let's say, different magnetic fields you have applied. So let's say you are looking at the magnetic property. So you have applied different strengths of applied field. Okay, and again for each of these fields, you will have like the spin state which are also involved. So if you look at for one particular sample, how many cases are appearing? So one is branching out into 5, and then here each one is branching out into another 1, 2, 3, 4, 5, 6. Then here each of them are again further branched out into 5, and then this 2. So it's like 1 will be in 5 times probably 630, 30 times 5. 150, 150 to 300. So each one is branching out into that many numbers. So overall, you can think of like how many data sets will be there. Okay, so clearly it is kind of quite a humongous task. Now in MATLAB, what you can do is that, let's say you have to import all the data. Okay, so and you have to do that day by day, or let's say in a systematic manner. Suppose here I'm assuming that you're doing all the analysis into MATLAB. Okay, so suppose you have sample S1 data 24 January and you have studied against all these parameters. So what you have to do is that you have to create a data file name in this form s1.24jan21.t300k.f1000 gauss.up, and here within the bracket you have the data which will be stored here. Okay. Now, here, suppose you want to write something in addition. So all you can do is that you can simply create another structure like up to 1000 Gauss dot info, like information. And then here within the bracket, you can write whatever you like. Like I did this thing under this condition. So it could be some kind of text. Okay. So what will happen is that finally in MATLAB workspace, you will get something called as S1. If you click on that, it will open probably this particular window. Sorry, go back to the earlier slide. Yeah. So let's say if you click on S1, then you will see there are 1, 2, 3, 4, 5 different new blocks will open. And if you open, suppose one of these, then another 5, 6 will open. Okay. And if you keep on clicking this, then finally on each of these, you will see that there is the data, which is XY column, which will be available. And if you have to plot it, what you will have to do is that, suppose you want to plot this data with down data. So all you have to do is that you use the plot command, like plot S1 dot this particular name you can copy, and then you have to take the first column and plot of this with the second column. Okay. So here actually within the bracket, you can specify what is the row or column you want to plot. So here, once you do that, you don't need to even remember that which date, what you did, because all the informations will be simply branched out. Okay, so it's like a family tree, and that way you can store as many number of data as you want, and MATLAB will efficiently store this thing. And if you even forget, like for S1 sample, how many investigations you have done, all you have to do is that you have to click on the tab button, and that will kind of open up how many days, like how many, like 24th, 25th, 23rd, 22nd January. So it will open, like it will tell you how many are available. So you select one, then you click on the tab again, it will tell you how many temperatures are available, and so on basically. Okay, so these options will kind of help you to define a data structure. So I personally have used it and I found it quite useful. So if you want, you can also do this. So it will actually save your workspace, and then but make sure that you have to use appropriate name, which are possibly scientific names. Okay, so now I'll go to one case study. So I have actually two. So this is actually slightly physics work. I hope you will not get too much kind of bored with this thing, but I'll try to go as kind of like a elementary level I'll start from. I'll try to explain as much as possible, but you please look at kind of like you please try to follow the workflow, how I mean this raw data has been analyzed and we have done some fitting, and then finally plots have been generated. Okay. So let us first, I'll give you a brief introduction of the system also. So I'm talking about neutron reflection. So reflection, you know already. So optical reflection, you know, like you have optical rays. So it could be some light that falls on a surface and it gets reflected. So neutron reflection is basically neutron beam. So as you know, basically within the atom we have neutrons. So there are some ways you can extract the neutrons. And I mean, you need basically some sophisticated facilities. However, it is possible. So once neutrons are out, they can be used for doing some reflection experiment, and they will give you quite a lot of information about the atomic structure of a material. So that is why the experiment is done. Anyway, so now the reflection process, it works on this way. So suppose you have a neutron wave, or let's say neutron beam or neutron that is coming and it is getting reflected. So again, if, let's say the wave vector that represents the neutron, or let's say simply it is the energy of the neutron, which is represented by this wave vector. So it's K incident. Then Kr will be the reflected wave vector and Kt is the transmitted wave vector. So these are the processes which actually goes on. And usually, if you, let's say, can count the number of neutrons that have been produced and the number of neutrons that have been reflected, then what you can do is that you can actually plot the reflectivity. That means, let's say, the fraction of neutrons that have been reflected as a function of Q. So Q is called as momentum transfer. So this is nothing other than the difference between Kr minus Ki, or let's say that difference between these two wave vectors. So if you plot it, let's say for a single material, So this is actually a flat, let's say 2D surface like a thin film. So you get this kind of a behavior. So you get a flat which is at 1, and then it will sharply decrease. So this is typically goes as 1 over q to the power 4. Okay, and there are some mechanisms like simple graphics which you can understand that if it's high energy, then the wavelength will be very small or frequency will be high, and then when it's getting reflected, it will have slightly different energy. So the amplitude and the frequency will be different, and transmitted will have a lower frequency. And as a result, basically there will be some energy change. That means Ki and Kr will be different, which means that there will be a Q. Anyway, so I hope this part is clear. That means we have what fraction of reflection is happening. That actually represented by this graph, and that is the main aim of this experiment. Now, there is something called as polarized neutron reflectivity. So here what is happening is that, so these neutrons, they actually are of two types. So one carries like up spin and down spin. So again, I'm not getting into what is spin for the moment. Let's say there are two categories of neutrons which are available here. Incoming neutrons can be of two types. So let's say one is red, other is blue. Okay, so these are red electrons or blue electrons, and they are actually sensitive to the magnetic behavior of these materials. So the more splitting between these red and blue colors, that means the material is more magnetic. Okay, and if you have a sample or material that has like more than one layer, so it could be like silicon, it could be cobalt, it could be nickel, something like that. So more the number of layers, more will be the number of oscillations. So each of these oscillations will actually correspond to the thickness of each of these layers. Okay, so you have basically one incoming beam that is coming, it is getting reflected, then part of is that is getting transmitted, again subsequently it's getting reflected, part is again being transferred here, it is getting reflected. So finally the net reflectivity that will be counted here will be a sum of all these reflections, and the transmission will also be similarly the added sum of all this. Okay, so that is the thing, and since this reflectivity is coming up because of this red and blue colored electrons, so I'll get a graph for red colored electrons and I'll get a graph for blue colored electrons. Okay. Now here this is one experiment which I have done, and then you can see that there are basically a silicon substrate and there are 1, 2, 3, 4 layers which I have, and I did this experiment, and after that I get this kind of data. So these dotted symbols are actually data, and these solid lines like these blue lines or green lines, they are actually fitted graphs, and so this fitting was done based on a model. So actually this model calculates the reflectivity that can be kind of like we have basically defined a model, and from the model we are calculating the reflectivity that is possible for such a system. So we have given some input parameters, and that we are trying to match with the experimental data just to see that at like what sort of parameters are actually getting into or let's say correspond to this physical scenario. Okay, so now I'll tell you, I'll briefly go through the mathematical part of the modeling. So this was taken from a paper which is actually almost now 30 years old. So it actually tells you about a let's say I have the system which has multiple number of layers. Okay, so let's say 1, 2, 3, 4, 5, n number of layers. And what it does is that it solves something called as the Schrodinger equation. You all are familiar with this thing. Those of you who are not too much comfortable with this, just assume this as a second order differential equation. It's as simple as that, because here we are not interested in we are not going to discuss the physics part, but rather we are talking about the numerical solution and how to find out the values. Okay, so this is a second order differential equation. So here you can see this is the del square, that means the d2, del 2 del x square, del 2 del a square, also so things. And this Vr is the potential, and then E is the energy. So psi is the quantity which is called as the wave function that we are trying to solve here. Okay. So here, since we have this particular geometry of the system for which we are going to solve this, which means that we have some symmetry, or let's say some particular condition. So here we are only interested in this parallel component of the wave vector. So we get this wave function in this form. That is, we can actually write it as a parallel wave function. So psi r will be psi of y times e to the power I k dot r. So this is the plane wave part. Okay, so again, I'm not getting into too much technicalities. So all I'm doing is that I'm substituting this wave function into equation 1, and I'm getting a simplified second order differential equation, which I can represent in this form. Let's say equation number 2. So this is d2y d2 dy2 plus q alpha square psi y will be equal to 0, where q alpha is this particular constant. Okay. So this is the second order differential equation. We all know what will be the type of solution it has. So it basically gives us a solution of this form, that is plane waves which are moving opposite to each other. And we have two unknown coefficients. And if we want to know these values of this, then what we have to do is that we have to have the boundary conditions. And since there are two unknown coefficients, we need two boundary conditions. So we put the boundary conditions, and then we can actually write down a general form of this. Let's say for any layer, that is alpha layer, this particular solution can be written in this form, that is A alpha will be the coefficient e to the power I q alpha y minus y alpha plus B alpha times e to the power minus I q alpha times y minus y alpha. Okay, and in the matrix form, I can write it in this form, that is 1R, and there will be matrix M1, M1, sorry, there are 4 elements, and there is T. So just keep in mind that R represents the reflectivity and T represents the transmittivity. Okay, so if R is 1, T will be 0. If T is 1, R will of course be 0. Okay, and then what we are trying to do is that we are trying to represent M coefficients. So there we have 4 in terms of basically this R and T. So we get a matrix. This is called as transfer matrix. So it very simply what it does is that it tells me that from layer 1 to layer 2, if I want to go, then the reflectivity, how it will change. Okay, so how much it will be transferred. And a general expression I can write in this form. And basically, yeah, here actually I can do a little bit of more manipulation. So let's say for alpha and alpha plus 1 layer, I can write this solution of this form. So you can see the coefficients are representing different layers, and I can do further boundary condition implementation, and then you can actually get these particular D matrices, which actually I told here that actually you can write it in this general form, and that will give you, let's say, a very general form of M in terms of something called as this Q vector. Okay, and this R you can actually represent by M21 by M2, Q2 minus Q1 by all these things. So in terms of Q vector, basically R and M and Q can be correlated. Anyway, so that is up to the thing where we do not deal with the spin part. So, or let's say red or blue part. So here, if we look into the spin part, then basically you have to look into this potential. And so if you remember that in the equation, I have a VR, which we actually put it into the expression for Q alpha. So here I have basically this term mu dot B, and it can take actually two value, because if they are both, these two vectors are in the same direction, or these two vectors in the opposite direction. So one will be added to this term, or one will be subtracted from this term. Okay, so if we do that, then basically earlier this 1 by R and T, these matrices are a 2 by 2 matrix, but now I have this spin, which means that another 2 degrees of freedom are being incorporated, which means the matrix will be 4 by 4 matrix. So this transfer matrix has basically 16 elements. Okay, and I can represent these transmission coefficients and reflectivities in terms of these M vectors, and finally I get a kind of like big expression like this. Okay, so basically these are the final expressions. So I hope you got the picture. So basically all I'm doing is that I'm trying to calculate the reflectivity by solving the equation, and finally I'm trying to get the values of these coefficients, which will tell me what is the value of reflectivity at a particular value of Q. That is why I want to plot. And finally I can also differentiate between the reflectivity of, let's say, red and blue color, and that is called as spin asymmetry. So this also can be represented in terms of this up and down contributions which are coming in the reflectivity. Okay, so basically what we have here is that we had a multi-layered system, and we are calculating the reflectivity. Okay, so now if I want to calculate that, first I have to define certain parameters which are basically describing the system. So this is a function that is called as layer structure. So here you can see this is a table where basically different elements which are used, there some values are kind of listed here, like A is the atomic kind of weight, and then rho is the density, n is the number density, then b is the scattering length, some parameters. So the formatting is not proper because I have taken it from MATLAB and the copying and pasting is not very proper. Anyway, so here what I'm doing is that let's say my structure has these elements, kind of this, my complete structure has these layers in this particular order. So here for this particular system, I have air, which is the top layer. Then I have tantalum, iron, manganese, niobium. Then I have, let's say, permalloy, then copper, silicon. And for each of these layers, I have 4 parameters. You can see in this order: D, rho, B, M, sigma. So these are given in this particular order. So let's say for tantalum layer, I have 50.05 angstrom. This is the thickness. 5.541 is the density. 6.91 is the number density. Of course, they have units. And 0 and 0 are the scattering length and this thing, because I don't know it yet. For air, these are all 0 because air doesn't have any density here. So that way I define a layer structure. So these are individual elements of the layer structure. So what layer structure does is that I incorporate all these different blocks here, which means that this will become a much larger size matrix. So you can see if you think of this vector, it has only 1, 2, 3, 4, 5, 6 elements. Okay, but here this will be a much larger size vector. So you have air, tantalum, iron, manganese, these things. Now the advantage here is that suppose I want to change the layer structure. Suppose I want to put this layer on top of this or that layer on top of that. All I have to do is that I have to change the sequence here into this command. Okay, so I don't need to do anything here. Okay. So this is my input parameter set. So it tells me what are the parameters that are there in my system. Now, what I do is that I take this layer structure and then I calculate the reflectivity. So I'm not showing you the script because it's quite big, but this script has been developed using the model which I described. That means we are solving this Schrodinger equation, that means the second order differential equation, and we are calculating this M coefficient, that means the M matrix, and from there we are calculating basically the reflectivities. Okay, the small r and small t. And for doing that, we need to have the different input parameters. So from there we get the reflectivity. And if we want to do that, then let's say I can change the input parameters, or I can add and drop different layers to simulate the reflectivity for each spin state. Okay, and once it is done, then I can overlay on experimental data for comparison. So I'll show you what was done. So this is the first part, that I have an input parameter set. Okay, that tells me what is the system that I am interested in or I'm working with. Next, what I did is that I took those input parameters, I calculated the reflectivity using that. And in that process, I might add or drop the thing, and whatever result I have got from the reflectivity, I am plotting it onto the experimental data just to see whether the input parameters or the assumptions that I have taken, whether they are valid or not. Okay. Next, what I'll do is that I'll do some sort of a fitting, and this is the basically chi-square optimization fitting. So here I'll show you the command, let's say the plotting function, or let's say the final command which was used to do the fitting. So there are certain number of parameters which are here in this bracket, and there are certain also parameters and things which are within the right hand side bracket. So let me just explain to you one by one. So there is something called as LM fit. So this is called as let me see, Levenberg Marquardt algorithm. So this is basically a nonlinear regression algorithm. So like you know that the chi-square you can calculate for a like kind of, if you have, let's say, particular data set and you want to do a least square fitting, then here also it does a similar thing, but it can also handle nonlinear systems. So that is basically it is doing, it is optimizing chi-square. What is the optimization? I have a calculated data and I have an experimental data. Using the sets of parameters and the function, it is trying to give you the best possible fit. Okay, that's what it is doing. And here I have AFE out. So this is the output parameter set. Okay, so if you remember that I have this A matrix here earlier, this layer structure has been given, and here actually this is the output parameter which have been calculated using the input ones. Okay, so that it gives me. Next is here actually this formatting is not proper. So here you sorry, actually on this computer this formatting has gone a little bit bad actually. Okay, so these arrows have moved a little bit because I actually made it on my laptop. Anyway, so let me actually explain it here. So here you can see that there are this FE underscore up minimum colon up maximum 1, then do minimum maximum 1. So these are basically the different columns of the data sets. Okay, so these are the actual raw experimental data which I am working with, or I am fitting it on top of that. So this is the let's say up spin, which means it's a red colored line, and this is the blue colored line. So this is column 1, which is the X column. Then this is the Y column, and this is the Z column, or third column. You can ask me, okay, what does this X and Y, Z, 3 columns are representing? So X column is representing the Q, Y is representing the reflectivity, and Z is the error bar. Okay, so these are the 3 things that are representing. AFE is the input parameters, okay, and AFE is the output parameter, which I explained. Then I have basically MFit, which is basically the number of parameters. So you can see there's MFit. So it is the number of parameters that I'm fitting. List A is which specific parameters I am fitting in the A matrix. So in the A matrix, I have like probably 70 or 80 parameters. So I'm specifically telling here that you take the 6th, 7th, 10th, 13th parameter and you optimize them. Okay, and here I have this script where it is this ref m NIFE up and then ref m6. So these scripts are actually calculating the reflectivity. Okay, so I hope these parts are kind of quite clear to you. So here this AFE is the output file, and then this chi-square is the value of chi-square, covariance is the covariance matrix, and LMFit is the Leventhal algorithm. So this is the mother script or the function name. These are the data files. Okay, and then AFE is the input matrix, list A is the number of parameters which I'm trying to fit, MFit is the total number of parameters, refm is the script which is calculating reflectivity, and 1e to the power minus 2, this is the tolerance, which means that up to which accuracy I need to keep on running this optimization for reaching convergence. Okay, so that is what I have done, and then once I have that, then I have to do some plotting, so data illustration. So what do I do? So here I see that there is figure 1, and the first command I am telling here is that to plot it on a semi-log scale. So semi-log FE up and FE 1 and 2. That means this is the raw experimental data. So you have the x-axis and you have the y-axis. So if you do that, let's say if you put this command, then you will get some sort of a plot like this. Then you type hold down, which means that you are asking this graph or plot window to holding on. It means that further plots are going to come. You please do not erase this current plot. Okay, so next you have this error bar, which means that it is still you have this error bar which is associated with each of these data points, and it is plotting simply those error bars using this particular plotting function. Now what you are doing is that you are calculating the reflectivity which has been using the parameters which you received as a output from the optimization. So earlier what I said you that A output, that A matrix you get as an output. So you are using that A matrix to calculate the reflectivity of basically, so you have the X and then you have this refm, that means the reflectivity calculation script. So you are using this output matrix, and you using that you are calculating the reflectivity which you can get from that, and you are plotting it on top of this. So you can see that this command plot up fit here, it is basically plotting the actually calculated, or let's say fitted graph or simulated graph on top of this black line. Okay, so now here I can see basically there is a good agreement, but however there is some space between these two. That means the fitting can be improved further. So you can further fit some of the parameters again. So like this list A and the parameters which are specifically in the A matrix, you can actually ask them to change it, and that will actually can improve after certain numbers of fitting, that this graph will basically match on top of the experimental data. Okay, so that will improve the quality of fittings. Now the same exercise you can do it for downspin, and there also you can plot the raw data first, then you can plot the error bar, then you calculate the reflectivity for downspin, and you plot the downspin reflectivity in a similar manner like this. And then you type hold off, which means that you are asking, okay, you don't have to store any more plot on this particular graph. Okay, so that is how you kind of create this illustrations. So if you remember that when I first showed my experimental data, there also you had seen, okay, excuse me, multiple lines, and that are basically generated by these sorts of commands. Okay, so now you have the output, but you want to keep this output in a let's say printable manner, or you want to save it in a way so that in future you can use it without much kind of like hesitation, or let's say you don't need to do too much work again to find out what is what. So you create an output file. So you can see there's this command sprintf. So this is printing basically. So you specify the path, and then in this percentage means you are asking it which format, like is it's binary or decimal or something, and output file. So this output parameter, whatever you have, you specify the name here in the from the workspace, and it will do with that. And then you can also specify output data, output figure. So all those things you can do, and you can save the output data also. Okay, so like your fit parameters, the fit metrics like a matrix, chi-square, all the fitted values. Okay, you can do that. You can save that data into this format, and also you can save each of these figures, like what I showed you in the earlier slide, that how you are plotting the experimental data, and then you are plotting the fitted data on top of this. Then what you can do is that you can actually also save these figures. So that way your output will be saved. Now this is a nice way of doing this. Alternatively, if you want to save the entire workbook, or if you're a little bit lazy, or if you are running out of time, then you can simply save the workspace. Okay, and also what you can do is that you can export this into a report format which is editable. So I'll show it to you at the extreme end. I'll show you one of my reports that I have prepared some time back. Okay, how these things can be done. So this is my one case study which I have shared with you. So I hope at least some things are clear here. Okay, so now do I have some time? Shall I talk about the next one?
Yes, you
can please continue.
Almost 20 minutes.
Okay. Okay, thanks. Okay, so in this part, this is again a work of mine. So here we are going to talk about vortex phase diagram. So now before getting into this, so this is basically, if you remember that particular figure which I talked about, the nature paper figure, there you have seen these colored images, like different branches which are coming out, and how these nice colored images can be produced. As I said, like these graphs will not be the raw data that you will get, but you have to take the raw data, and if you process it in some certain way, then actually you can plot these things. Okay, so now for getting into this, I will also go through some of the basics, but these are a little bit more elementary. So this vortex system actually is actually observed in some systems which are called as superconductors. Now, why did I take this particular example? Is because the phase diagram is quite colorful and interesting, and you can see different colors. That is why I took this particular example, frankly. Okay, so you probably have heard about superconductors. So this is a particular kind of material where actually there is no resistance. So whenever you are trying to pass a current, then the material does not offer any resistance, which means that current can pass without very freely. However, you need to cool this material below a certain temperature that is called as critical temperature. Okay, so once the material is cooled below this temperature, this disappearance of resistivity is observed. And it has basically some interesting aspects. So if you look at the magnetic behavior, so this is the temperature on the x-axis and magnetic field on the y-axis, then you can get actually different kind of magnetic behavior. For example, here you can see like whatever magnetic field lines or flux lines you are applying from outside, the sample will completely eject them. That means this will be a diamagnetic kind of behavior. However, if you like kind of extend the magnetic field or increase the field, then you will get a different kind of state. So this is called as the vortex state, which we will discuss actually. and related to that there are certain parameters. Okay, so now what happens in this second part, which I just said here, like this abricos of state. So this is also called as actually vortex state. So here, when you are increasing the magnetic field, this magnetic flux, like actually whenever you have a field, that means there will be some magnetic flux lines. They start entering into this material through something called as quantized rods of flux. That means some small lines, you can see these arrows, so it will try to enter into this material, and each of these lines, they will contain certain amount of magnetization. Okay, so this is H by 2E, so this is Planck's constant, this is electronic charge. So that is how basically they enter. Okay. Now, usually these flux lines, they have basically certain normal electrons, and anyway, there is some supercurrent which will be generated. So we'll not get into this. And this particular phase, that means where you have multiples of these green and yellow lines, this is called as a vortex phase. And usually they will repel each other because they are magnetic, so they will repel each other via something called as a Lorentz force. So this is like E v cross B. So those who are from physics, they can relate it to. And the reason that they, not reason, basically the fact that they repel each other, it is actually quite interesting, because that is why you see them arranging in some particular format, and that will give you some interesting phase information. So if you look at this kind of, so what we have is that to have a superconductor, we apply some magnetic field, we have flux lines here, and then we have these lines which are repelling with each other, which means that they have to distribute themselves in some particular structure. So you can think of it here in this case, they have arranged in a triangular lattice. So at each corner you have a flux line. Okay. And now if I want to know that what is the basically magnetic profile of this particular lattice, okay, of the system, then here when you have these bright spots, you get a very high magnetic field. However, when you are in between these two, then you get a low magnetic field. So you have a high, low, high, low. So it is kind of like a mountain and valley kind of picture. Now, there is actually some experiment which you can do. So there are some basically like let's say, okay, so let's first talk about this. So suppose you have a some elementary signal, which let's say it's a sine function, which is function of time, and if you plot it in the frequency domain, or let's say in the kind of like frequency domain, then you will get basically you take a Fourier transform of this, then you get a peak. Okay, so this peak is basically, so this is like a sine omega t, so you will have a peak at omega. Okay, because you have only one frequency. If you have multiple frequencies here, then you will have multiple peaks here. Okay, so here basically there is some experiment which can be done. So you apply some particular waves, and that will kind of have a time dependence like this, and that oscillation, which means that this kind of like there are some like neutron-like particles, these are called as muons. So you can actually use them, and they will have a time decay like this, and that decay will be proportional to the frequency of this decay will be proportional to the flux density. So you can see this B equal to omega divided by gamma. Okay, so if you do that, so let's say we have these muons, which I was telling you, they will come and they will basically jump on your material, and as a result, what you'll get is that, so this is the time decay of this signal. So you can see the amplitude actually drops quite fast over a very small time scale. And if you want to plot the probability of B, so here actually what we have here is that you have only one field. Okay, however, here if you look at, there are different fields. So this is a high field, this is a low field, so there are multiple fields here. So if you actually take the Fourier transform of this time domain signal, then you get multiple frequencies, which means that multiple B will be present here. Okay, so you get a peak, and then you get a distribution here, so it's a low, and then you have a high tail here. Okay, and from there actually this shape size of this particular distribution will tell you a lot of information. Okay, so for example, this particular part of this field profile will correspond to that particular point here, and then these peaks will correspond to the maximum. Then here this kind of in between two peaks, this flat line is corresponding to the peak. Okay, and so on. Okay, so now from here what you can do is that, so you have this line shapes, that is PB versus B, So that's just I showed here. So this is basically P of B and B here. Okay, these are called as line shape. So now once you have that, then you can calculate these parameters. So this is called as this is the third moment. You can see P bi and bi minus b cube divided by sum over bi. And the second moment you can calculate. So this is, let's say, the standard deviation, and this is the third moment, and the ratio of these two you define as alpha. Okay, and from that you can actually say if it is greater than 0, you have some phase. If it is less than 0, you have some particular phase. Okay, so that's how you can actually analyze the data. So keep in mind that the raw data was about a time dependent signal. Then what you did, you first subtracted the background and everything that I didn't cover actually. But once you have that, then you took the Fourier transform, and then from that we got PB as function of B. And from that PB, we have calculated different moments. There's second moment, third moment, and from that we calculate alpha also. That is the ratio between 1/3 of the cube root of the third moment and second root of the second moment. Okay, so this is a dimensionless quantity. And here I am trying to look at what is the value of alpha for each of these cases. Okay, so I hope the picture is clear here. Now, I'll tell you what sort of systems, or let's say what sort of situations can arise here. So earlier I told you that there are these flux lines. So these are like solid lines which are distributed in a triangular lattice, and we get these peaks. However, sometimes they are not necessarily like a kind of like long solid line, but they are into broken pieces, and they are along the same axis. So these are called as pancake vortices. So this is what we are assuming. However, they are actually split into different parts. Okay. Now there will be some repulsion between them, and there will be some attraction between them, and sometimes there can be some pinning, which means that these layers move and then they cannot come back. So they can happen also. And as a result of that, there is something called as irreversibility, which is observed. Okay, so it means that they go, however, not all of them can come back. So this pinning actually means that there are some, let's say, defect or some impurity. So these vortices don't move anyway. So that's why they're kind of come to something called as a glassy state. Okay, so there is more disorder here. So these are a little bit more complicated terms. So that's why I'm not getting into this too much into details. I'm just explaining here just so that it will help you to understand the phase diagram. Anyway, so then there is thermal disruption, which means that if you have more temperature effect, then basically they can also move. Anyway, so finally what I'm looking at is that I'm trying to find out at what temperature and what magnetic field, how do these flux lines or vortices they will behave. So usually when the temperature is low and field is low, they're aligned in the same direction, which means that they have a nice periodic order, like similar to the triangular lattice as I showed at the beginning. So this is called as a solid phase, vortex solid phase. And then if I increase the field but keep the temperature same, then you can see there is some movement of these vortices, these pancake vortices, from their mean position, or let's say solid phase. So there is some glassiness that actually arises. Okay, so this is called as a glass phase. Okay, so remember, this glass phase is something which is not solid, not liquid, which means that there will be some periodicity, some say correlation, but it will be smaller than the solid phase. Okay, and then there will be liquid phase, where if you go to high temperature, then you can see that the vortices will be moved away from each other. So it is like a liquid phase. So the periodicity will be little less here. So this entire phase diagram is called as vortex matter, and they have quite a lot of applications in different areas. Now here I'll show you some of the examples of real life examples. So here you see that this is the diagram which you can get by plotting this parameter, that is the second moment from this PV. Okay, so you can see we have this red colored region, yellow colored region, and this blue colored region. So we have two different lines. So it is similar to the ones here. You can see these lines set here. So one is called a disordered line that separates between the solid and glass phase, and liquid phase is separated by these blue lines. So here also we are showing these same lines. So here this vortex lattice, that means the solid part is represented by this, and then basically, yeah, this is also another experiment where we have actually confirmed this anyway. And then we have this part is also existing in here also. Now, yeah, so this is a nice diagram where you can see that we have this solid lattice part that is complete red color here, and then we have this glassy phase that has this slightly kind of like yellowish green color, and then we have the liquid phase which is completely blue color. So there is a clear color difference between these three phases, and that you can actually clearly see here. Okay, and on the z-axis you see there is some value. I think this is the second moment, that is the sigma here. Okay, so if you plot this, then you can actually get to this particular figure. And here if we plot alpha, which is the ratio between the cube root of the third moment, so this is actually a mistake there, there will be third cube here, so cube root of third moment and square root of second moment, then you can clearly distinguish between these three phases. So you can see here that you have this vortex lattice phase, that means this clear red color is here. Then you have basically some medium range correlation. Okay, these are like some contour plots which have been made from here actually. And then you have this glass phase which is here, that is given by the yellow color, and sorry, and then you have the liquid phase which is given by the blue color. So as you see that clearly we can distinguish between the different phases, although this is the information which was not at all visible when you look at the raw data. That means it was a time domain signal. That means y as function of t basically, or ft as a function of t. Okay, so if you do a little bit of analysis and a little bit of manipulation, kind of like plotting or representation, then you can actually arrive at this point. So you can see this alpha has some range, and if you change the range, then basically this color pattern will also change accordingly. Okay, so with that I will almost come to the end. So there is this third part. I'll not actually explain much, but this is also some sort of a phase diagram, but I'll just show you the diagram so that you can see. So here actually this is a particular system where this left hand side, this is the experimental data, and the right hand side is the one which I have actually simulated. Okay, so you can see they're almost falling on top of each other, but I didn't plot it on top of each other because then it will not be visible. The only difference here is that here you can see some spots here, like these bright spots here at the background, which is absent here. That is because when you're doing an experiment, you will get some noise, of course. Okay, but here in computers, not when you're doing a calculation, these things you can easily take care of. Okay, so you can see this x range and the y range, they're basically same. The level of current is also same, and it is actually possible to do this thing. And entire these things are, I mean, whatever I have shown so far have been done with MATLAB. So with that, I would like to summarize here that MATLAB is quite useful, which you have understood by now, that for data illustration and plotting, and it is a very advanced level scientific programming. So you can actually do quite a lot of advanced stuff with this. And you can do graphic preparation and data fitting, data analysis, everything. And there are options of doing GUI preparation and interactive fitting. Okay. And finally, the last point, which I promised you that I'll show it to you at the end. So this is called as document preparation. So I'll just show you here if I have it. Okay, just try to see it here. So with that, I'll finish actually. So okay, so let me just try to escape it here. Sorry, it is not actually going there where I want to go. Okay, so let me just stop sharing for a moment. And
Dr.
then
Soumya, we have two questions are there from the participants.
Okay,
are you
sure,
getting
sure,
my
sure.
voice, Dr. Soumya?
Yes,
So
yes, yes, I can hear your voice.
From the there are a few questions from the participants. I think I would like you to share with you these questions, and then you can answer
Okay.
these questions.
Okay.
Should I go ahead?
Yeah, please, please, please.
So first question is by Ms. Nikita Barpe, and she has asked that how to share coding file of MATLAB. How one can share a coding file of MATLAB.
Okay, so this is, you can simply email.
Okay.
But you can say, I never did it, but I think you can share it with WhatsApp also.
Okay. So there is another question by the same participant, by Ms. Nikita Barpe. the question is where the contour plot is used and how that plot will be analyzed.
Okay, so as I said, the contour plot is quite well used in the case of let's say in many cases, like in reality, I'm saying in weather data analysis, like whenever you see like that some storm is coming or some tsunami is coming, then you can see wherever there is a pressure buildup, high pressure zone, low pressure zone, and how the streams are going to move away. So this is one typical example where these contour plots are quite useful. Or let's say fishermen, when they go to sea for fishing, so they are sometimes what they do is that they use ultrasonic sound just to know where the fishes are there. So that also, I mean, they actually get some contour plots. I mean, it basically produces, and that tells us like how fishes are swimming in the water. Okay, so there are these are the some of the examples.
Okay.
Okay.
There
is one
is
more question.
another question from Dr. Mohammad Zakawallah. He has asked that how to draw surface graph with error bar.
Surface graph with error bar.
Yes.
I mean, can you give me one example? What sort of system you are looking at? I mean, thinking of.
Okay, I'll ask Dr. Mohammad Zakawallah to raise his hand so that I will switch on his mic so that he can ask the question directly.
Okay, okay.
Okay, Dr. Mohammad Zakawallah, you can ask.
Hello, good afternoon, sir.
Good afternoon, yes.
Sir, actually, we draw a surface graph wherein we try to go for an error bar with because experimental and what we have from the modeling ANN. So we just see what is the error generated there. We go for that error bar, sir, during that.
Okay. So
Modeling result and experimental, sir. What is the error? We just go with an error bar in the surface graph.
Okay, so usually see, I mean, if you have a line plot, let's say y versus x, there if you plot the error bar, it will be clearly visible. But if you have a surface plot, that means it is already a colored surface. And
Yes,
if
sir.
you want to plot the error bar on top of that, I mean, it is possible. It is not impossible. So you have to basically, all you have to do is that, let's say you have x, y, and z, right? Three variables. Sorry, three variables, let's say. Okay.
Okay, sir.
Right? So x and y, let's say, are your independent variable, and z is the one which is basically calculated, right?
Okay, sir.
Okay. So now all you have to do is that you have to define a function. I think MATLAB, there might be an inbuilt function, but you can simply define a function like, let's say, some error bar which you have calculated. All you have to do is that you take the z value, you create half of that. I mean, whatever error. So let's say delta z is the error which you have got. Okay.
Yes.
So all you have to do is that you have z, which is the value that is actual value, z plus delta z by 2 to z to delta z minus 2. Okay.
Okay.
So that is basically like you are putting z at the middle, and then you are putting a range of plus delta z by 2 to minus delta z by 2 above and below it. And if you do that, and if you just plot that those two bases, so you have to create, you are getting two values here. Okay.
Okay.
So you can create a marker plot on that, and it will plot you on top of that. But I don't know whether it will look nice or not, because on actually surface plot, error bar will not look very nice.
Yes, we have done in Origin, sir, actually, but they are charging.
So here all you have to do is that you have to define this error bar. So I told you the basically process. So you just need to add this error with like half of that error and subtract it. So you will get two values. So you have to tell it that, okay, this is the maximum minimum. You just plot this on top of that.
Okay, sir. Okay. Thank you.
Okay.
Thank you, sir.
So if you have any question, actually, you can email me. I mean, I can actually
Please,
help
sir,
you.
show yeah.
Okay.
Kindly display email so that I can send you that, sir. I have worked on that, sir. I have used Origin actually.
So in Origin, I cannot say now because I never.
No. I have worked, sir. I have worked on Origin,
Okay.
drawing surface graph with error bar, but I find difficulty in MATLAB, sir.
Okay. So if you have, you please. I mean, I will actually. Okay. So I'll share my contact details actually.
Yeah, please, sir, so that I can email you with the correct.
So I don't know why it didn't save actually. I wrote it here. Okay. So can you see the screen here?
Yes,
Is my
yes,
screen
yes,
visible?
Yes, sir.
yes.
Okay. So my email is this. Okay.
Sir.
This is my mobile number. Okay, and this is my web actually. Okay, so
Yes.
you can contact me in any of these. I hope this is visible now.
Yes, sir, it's visible. Thank you, sir. Thank you.
Okay.
Okay, there is one last question from the participant.
Yes.
He wants to know about the 4D visualization. Is there any 4D visualization?
4D.
4D, yes.
Okay. So you have to tell me the specific case actually, in which way you are looking for. Like, is it some 4 vector or something?
I will switch on his mic so that he can ask me. Okay, Dr. Sunil, you can ask your question.
1 minute, sir. 1 minute. Am I audible?
Yes.
Sir, it is related to plane mapping available in MATLAB help. This talks about quality volume visualization.
Okay. So you see, I mean,
Slices.
hello.
Dr. Sunil, can you ask again because your voice is not clear? Can you ask again, please? Sorry, we can't hear you. You are inaudible.
Hello. Am I audible now?
Yes, you
Yes,
are
you're
audible.
audible.
Yeah. It is related to MRI imaging,
Okay.
where we see the slices of the brain mapping. I suppose it's a very popular MATLAB promotion initially, which they have done along with visualization help. So they talk
Okay.
about 4D volume visualization.
Okay.
So are
Okay.
there any special functions or exactly
Okay. See,
higher dimension?
as of I have not used it, but I think if you want, then what you can do is that you can create a custom function. So it's like you have to have like 3 different independent variables and 1 fourth variable which is dependent.
Yes.
Okay, so it actually depends on like which way you are, like what type of data you have. So I am guessing what they're trying to do is that probably they have a 3D surface, and within the 3D they have more information which is located there.
Yes,
So
absolutely.
they're probably
Absolutely.
taking a cut, and that itself will produce another 2D plot.
Yes.
Okay.
Yeah,
Yeah,
absolutely.
so as of my knowledge, I mean, I have never used any 4D function, so you can probably try to write something. Okay, but those ones, I think probably this is custom made. They have like very sophisticated kind of like, I mean, you have to look at what type of data set you have.
Okay. Thank you,
Okay.
sir.
Yeah. Okay.
Okay,
So
so
now we are very much thankful to Dr. Soumya Jyoti Rai again for sparing your precious time and making such a nice presentation on scientific data analysis and visualization using MATLAB. And I hope that this presentation would would prove helpful to the participants in a larger way, and they will get benefit from this knowledge. So thank you once again, Dr. Soumya.
Okay.
And
Thank you.
in future also we'll hope to have you back again sometime
Oh,
and
sure.
have interaction with you. Thank you.
Okay.
I pass on
Okay.
to Dr. Danish.
Okay.
thank you, Dr. Ashraf
Thanks.
Sen.
Okay.
Okay, thank you, Dr. Ray, for accepting our invitation and delivering such a wonderful lecture.